to sensing, because the sensing device to sense the fault current and the relay operating time. And once relay operated, there is some logical operations, everything's going to compute over there in my relay. So once relay is decided, okay, this is a fault, so okay, I'm going to trip, means it will give the trip command to the breaker. Thereafter, breaker has to start its, in between that, okay, there are some supervisor relays, there are many relays are interconnected between my overcurrent relay and to the breaker. So all these relays will take some milliseconds. So after that, my breaker, it will take some time to trip. That is maximum 40 milliseconds. We are going to see that one. These are some unavoidable delays will be there in the system. So that is called inherent time delay. Except this time delay, I'm not going to add any intention time delay, means that is called instantaneous operation. So this is a relay suitability. That means that you have to evaluate before you are going to use any ETAP model. So you have to evaluate all your library and your vendor catalog, which is you are going to employ in your site. This is an important equation. This is a relay time calculation. I'm not going to talk in much detail. This is as per IEC 60255 151/2009 curves, and it will help you to which curve I have to choose. That means that you have to reduce your relay time, relay tripping time. So you have to find out that, so at what current, at what time is going to operate. It will be calculated by using this curves. Actually here I showcasing only the IEC, but there is the IEEE and ANSI. It has different formulas, and from that formula you can able to get the constant values. I will have one. This is the values you have to take from here. This is IEC and this is IEEE. What is the values of the constants? These constants you have to use with respect to your curve, which curve you are going to use. Finally you are going to calculate your relay operating time. For this current, for this is my scenario, this is actually my fault current is 132 ampere. For the load, depends on the load, okay, I have set my relay as 33.7 amp, and this is my TMS, okay, I have choose my TMS as 0.6, and I have chosen curve is standard inverse. In this case, okay, what will be the relay operating time? So I have to calculate, my curve is IEC curve, this is my formula, and I have take all these values, alpha, beta, and k, from my catalog, the standard values, and finally my relay operating time I have got is nothing but 3.04 seconds. Once relay got the fault current as how much? It was 132 amp. Okay, it will operate after 3 seconds, because this is nothing but normal inverse and standard inverse curve. It will not trip immediately. So that means that the answer says, so when fault current occurs this much, for my set current is 37, my fault current is 132 amp, but the relay takes too much time, is nothing but 3 seconds, 3000 milliseconds. 3 seconds means this curve is nothing but time delaying curve, is nothing but time moderate. It will not trip immediately. This is actually what we simulated with the ETA. For that same current, when I apply to my ETA, and finally we got the same answer. So for 132 amp, okay, relay operating time is 3.04 seconds. So relay suitability is very important. After that, relay priority. This is not a mandatory. We have to follow as per this slide, but we can give the priority from the lesson learned from our experts. TOC curves, okay, priority selection, where I am going to use my curves. If it is source side or if it is your incomer side relays, okay, widely you can use for standard inverse. Why? Because we saw just now it has some time delay, because since it is nothing but a source or incomer. So your downstream breakers, downstream relays has to operate first. After that, if it fails to operate, then your incomer relay has to operate. That's why we have to consider nothing but your trip time moderate type relays. Protection function is nothing but your TOC curves, and C code is 51. If it is equipment, and it is your load end, this is your load side, this is your dead end of your system or network. So where we can use either any inverse type, any inverse curve. Widely we will go with extreme or long inverse or very inverse. So this is the one. So we have to choose based on your load starting as well as loads damage curve. There is two curves will be there for the load. If it is motor, okay, we have two curves will be here. I can able to see in your ETAP. If you open your ETAP, there is the motor. There's a motor. If you go to the protection tab, so this is the one actually we are going to talk about it. This is actually your this is nothing but your starting curve, and this hard start and cold start where we are seeing this blue color and red color curves. It is nothing but damage curve of your motor. So like that, okay, each and every equipment has its starting curve as well as its what is that? It's damage curve. We can say withstand curve. So in between that, okay, you are going to fit your motor relays, motor curves are here. This is the one important. So I'm going to give these values and then give the stop in 15 seconds, and everything's here. So we go to the relay coordination. I can able to see what is the curve is applied over here. So this is my motor starting curve. So I didn't give I didn't consider any relays over here. I have chosen only my motor. My motor capacity is 355 kilowatt, and this is my motor starting curve, and this is my motor damage curve. This is nothing but hot curve. If you click here, okay, you can see able to see cold curve also. So cold curve also the same value I given. So it's supposed to give some little bit high value. So 22 seconds. This is nothing but cold curve. This is nothing but hot curve, and this is nothing but my starting curve. So what do you mean? This is my LRC, locked rotor current. This is my starting current. So once the locked rotor current come to here, and it will reduce. This is actually this is a full load current. This is full load current. And this is my starting current, and this is the time of your starting. How much you given? Okay, 5 seconds we are giving here. The same value will be displayed here. This is 5 seconds. So for 100% voltage, okay, my accelerating time is nothing but 5 seconds. If I apply my voltage is 80%, okay, then my curve will be different. Two curves will be here. Okay. So this is 80% and this is 100%. So how much percentage of voltage you are going to apply in your motor terminal? So based on that, okay, your relay time is different. Relay time, your motor starting curve is different. This is actually you have to apply your motor protection relays will be between these two. Between these two, we are going to see in our slides. So this is the priority. So for IOC curves, okay, where the source and incomer side, okay, you have to add time delay because when even the fault current is flowing through your relay, so relays are not supposed to operate immediately. So you are adding intentionally time delay because your downstream load side relay has to operate at first moment. So this is the reason behind, okay, we are adding some time delay in your source or incomer in some equipment side even. But load, this is a dead end load or dead end equipment means, okay, this end of your network means, okay, there is no intentional time delay will be allowed, and you can say that there is no inherent time delay. Only only there is some intention. There is no intention time delay, so you can allow your relay. You can set your relay to operate immediately. This is actually as per Alstom P141 relay. If you take one relay, okay, these are the curves will be available. So you can choose for phase, and you can choose for neutral, and you can choose for ground. Actually, what we are seeing is nothing but this overcurrent, phase overcurrent. And if we are going to give your neutral current, if you are going to give the protection against the earth fault means, okay, you are going to use either neutral or ground. So which your element, your sensing element, which is connected to the ground part, where you are going to give the protection against your single line to ground fault, but your detective device, your current transformer, which is connected to the part of ground connection of your equipment, and you have to use ground. If it is phase CTs, the same phase CTs you are going to use for the ground fault protection means you can use for neutral protection. That will be discussed in very detail in our detailed sessions. This is actually a protection function which is present in our Alstom P141 relay. And 50 operation, 50 function is nothing but instantaneous overcurrent. So here also the phase, any instantaneous overcurrent and the neutral overcurrent and the ground overcurrent is available. The same CTs will be used for the same operation, and you can use for instantaneous protection function. The standards for relay coordination. This is actually exact standard which we are following for relay coordination. IEEE 242/2001. It is called, is widely called as Buff book. We have many color books in IEEE, so you are well familiar with that one. So this is IEEE Buff book is an important book for recommendation practice for protection and coordination for industrial and commercial power system. And we have one more standard is 141/1993. It's a recommended practice for electrical power distribution for industrial plants. So we have to refer these two standards primarily. And we have some newer version of this IEEE 242 standards as IEEE 3000 series, and we have many standards are there. Even 3000 series already right now it is already published and we are using that. But even though, okay, still the Buff book is still in active condition. It will not any revoked or it will not removed from the industry. Still we are using that one. This is not amended, but it's giving the new form. But it's still we are using that one. There are the different standards. The standard IEEE 242 is only one Buff book for all protection, but IEEE 3000 series is elaborated and a little bit briefly explain about it in independent modules as independent modules. For instrument transformers, okay, we have one standard is something but 3004.1 2013. And bus and switchgear protection is, you can refer part 11, and applications for ALB circuit breakers you have to part 5 and 2014. And for motor protection, okay, you have to go for 0.8 2016 version. And which equipments we are going to cover here? Okay, the major we are going to cover if your microgrid system is consists of transformer and your load is motor. Then my protection is nothing but overcurrent and earth fault. As I mentioned before, okay, we can use CT as the important device for your relay coordination. Since current transformer is nothing but your important relaying device, sensing device for your relays, if in case of in medium voltage. So for phase overcurrent, for earth, for any ground or neutral, okay, you have to use the CTs for input, CTs as input. So sometime in phase CTs, okay, can be used for ground operation, and otherwise, okay, you will have your sensitive current transformer. Sensitive current transformer is nothing but core balance current transformer. Some industry and some terrain, It is called as a toroidal type current transformer. It is nothing but quite high sensitivity, which is we already discussed in our earlier slides. It's nothing but sensitivity is important in our relay coordination. That sensitivities will be achieved by your sensing device. Is nothing but your your CBCTs. Okay, where you have very lower magnitude of your earth fault current is there. There you have to supposed to use your CBCT. Otherwise, you can go with go with your phase CTs. Of course, phase CT is already configured for phase fault, phase current sensing. But the phase CTs, the same phase CTs, okay, going to configure for ground also. That is the one. Okay, this slide is explaining here. To be honest with you, okay. And sometime for ground fault, instead of phase CT, okay, we will use some dedicated ground fault CT. Ground CTs is nothing but a CPCT. Okay, it is widely is a high sensitive current transformer. It is called core balance current transformer. It is going to sense the ground fault current. Where my system is earth resistance, the system. The fault current is limited from 100 amp to 800 amp. This 100 amp to 800 amp is based on your rotating devices which is present in your system. That means in your medium voltage, there is medium voltage motors is there, nothing but high voltage motors is widely called sometimes medium voltage motors at 11.8 kV, and you start from 4.16 kV. Okay, I'm telling that ANSI course. Okay, the voltage levels are ANSI course. Because I work with ANSI standards widely in Saudi Arabia, so that's why I would like to say that's the same standard which is following, which I saw in practically there. 4.16 kV and 6.6 and 13.8 kV is widely we are using middleist voltage levels for distribution level. In that level, okay, we are using medium voltage motors. Where that motors is employed there, that motors stator curves with you will supposed to saturate at the level of either 80 amp or 100 amp or 150 amps. If once the ground fault occurred in your motor, the medium voltage motor, if the fault current flowing through that my stator core, what will happen? My stator core will go for saturation beyond 150 amp or 100 amp. So in this case, okay, you are going to limit the fault current. From either 100 amps. If your motor will get the saturation, your motor stator core will get the saturation at 80 amp means, okay, you are going to limit the fault current at 100. And if your fault current is, if it is, not 100, it will be going to less than that one, and sometimes 50 amps. If it is 100 amps or 120 amps, okay, your core will get saturated. So less than that current, okay, you are going to limit your fault current. So 120 current flows through your core will get saturated. Means, okay, you are going to limit fault current at 100 amps. So for that 100 amps, okay, you are going to design the resistance value. So you are going to add in your network. So I will check this one. It can be simulated in VTAP. So here this is actually a solidly grounded system. What we are talking about, this is the one. This is nothing but a solidly grounded system. But my voltage level is 13.8 kV. Okay, and here my voltage level is 4.16 kV. Okay. This tagging, okay, I consider this is the one motor. So this is a medium voltage motor. So I must be going for this grounding, and I must go for this is not the recommended grounding system. So system grounding is important because in downstream I have rotating machineries, I have motors. So when the ground fault is occurred, when line to ground fault, one phase is grounded inside of your motor, means the fault current will flows through your stator core, and if it is going beyond 100 amp, okay, your stator core will get damaged. So in order to avoid that, okay, you are going to limit the fault current by means of converting your right now is solid grounded system into resistance grounded system. So resistance grounded system means, okay, how much amp you are going to limit means 100 amps. 100 amps means, okay, that's already designed is, okay, you have to add 24 ohms resistor you are going to add in your neutral point of your transformer. So in this case, yes, yeah, Bala.
Sheikh sir, can you verify whether your screen is shared or not? For me, it is not visible. What about others? Can anyone able to see screen from past 3 minutes? Dear participants.
Ma'am, Nagalakshmi ma'am. My screen is visible?
Yeah, now it is fine, sir. Now it is fine.
Okay. So now probably heat up screen is visible, right?
Yeah. So let me.
Okay. Thank you, Bala. So my system is now converted into solid ground system into resistance earthed system. So resistance earthed system is nothing but, okay, I added 24 ohms resistor in between neutral point of my transformer and your ground. So now my fault current, single line to ground fault, any one phase to ground, when one phase is get grounded, okay, inside of my motor, okay, its fault current will be limited up to 100 amps. So beyond 100 amps, okay, it never ever flows through my system, because the earth fault current is already limited. So in this case, you are not supposed to use your phase CT as a ground CT, as CT. So what you have to do, you have to add your phase CBCT here, phase CBCT here. That is your primary requirement here. For that you have to use CBCT. How you have to convert the same CT, because we have any separate CBCT in your ETAF. You have only the model of CT here. You can convert into CBCT by means of okay, you just click down here, okay, and you have to use as CBCT. CBCT means, okay, all lines going together. This is important. CBCT means what? Okay, all three phases will go together. Usually in CT, what is the basic principle means? So one CT for one phase, and only one conductor will allow through your CT. So which conductor you are going to measure the current? Which conductor you are going to measure the current? Okay, only one conductor will allow through your CT. That is the usual procedure. But when it comes to the CBCT, is quite different. Okay, all outgoing phases of that particular equipment, which equipment you are going to protect. Okay, all CTs, all phase conductors, okay, we have to allow together in your CBCT window. Even if you have neutral, if it is a feeder for one downstream switchgear or motor control center or any panel is there, means if we have neutral in that particular feeder, so that neutral also you have to include it in your CBCT window. That is actually the connection philosophy of CBCT. And you have to add the CBCT here in your line. Okay, then you have to connect the CBCT to your relay. So you are added for phase. This is a phase sensitive, and this is nothing but your ground sensitive. So two values will be here, and you are opening your relays, and you are assigning. Okay, for phase. Okay, for phase. Okay, already added. For phase, for the sensitive ground, okay, you are adding CT2, and for even ground also, I consider CT2 is giving the ground current. So phase values will be sensed by your CT, and ground currents will be measured by your sensitive. Then now go to the output. Okay, you are adding one stage of output. Okay, then and you are going to configure the relay, and the relay name is CB1. So this is nothing but HECB, because this is 4.16 kV. So this is called HECB. And the breaker, so which breaker we are going to configure is nothing but CB1. And when fault occur, okay, what action you are prefer, either open or close. Okay, here you can give 3 options. Okay, because it is in closed condition while I'm doing the simulation. So I would like to prefer that one is nothing but, okay, when fault occurs, we are going to open. So this is actually you have to add, and now you are going to add the relay. For motor, okay, I'm choosing ABB relay. So the protection type is motor, and function is nothing but overcurrent. I'm not going to discuss with overload. Overload is overload distance differential. But distance we are not going to use, but differential we can use for motor, because distance is widely used in transmission lines. But differential, okay, we can use for transformer and motor as the meaning of unit protection. But here we are going to use only overcurrent. I'm sorry, I didn't choose the relay. Relay is nothing but REM615. I'm choosing. Okay, protection type is motor, and the function is nothing but overcurrent. Overcurrent is the non-unit protection. And this is actually value of this one. I'm not going to use negative sequence. Okay, I'm going to use only the 4 operations. Only nothing but overcurrent and instantaneous, and the ground, overcurrent and instantaneous. So we have many formulas for this one. So as it is the load side, so I'm going to use long inverse curve. And what about my full load current is here is nothing but 57.10. So I will add just 10% of this full load current. Only I'm adding 10% of this full load current as my overcurrent. What I am assuming, you can give 10% to 30% as overcurrent, not overload. There is a difference between overload and overcurrent. I'm talking about overcurrent. Overcurrent in the sense, okay, I'm adding only 10%. In Middle East, okay, we used to add 30%, but in India, okay, we are going to use only 10%. It depends on your client also. Whenever a client requested it has 25%, okay, you have to add 25% of your full load current and divided by your CT ratio. And CT ratio here based on your full load current, you have chosen as 700:1. Because the 57.1 into 1.1 is 62.81 amp. So I have chosen the market available immediate size of my next current is nothing but 62.81. So available CT ratio is nothing but 70:1. So when 70 ampere flows through my circuit, okay, my conductor, and it will give the 1 amp as the secondary, is going to sensed by my relay. So what is the formula? So I will go with my formula page in our what is that? Yes. This is actually for 51. Okay, 51 you have to use this one. I will go to the motor page because I don't have time. I think it has the biggest topic for this. For a very short period, I could be able to complete this one. But okay, this is actually the correct formula for 51. So what is the pickup setting for 51? So here this is actually what we are seeing in our ETAP. For that one, okay, you are going to choose your curve. As well as you are going to give the pickup settings. This is the pickup setting. Pickup setting agreement, okay, we have to add 1.1 of your full load current divided by your CT primary and CT secondary. It's nothing but in our case, my full load current is 57.1 into 10% you are adding divided by your CT ratio is 70 divided by 1. So my pickup settings is nothing but 0.897. Okay. Time dial, okay, I'm not touching now. Okay, time dial is important topic. And for manual calculation, it is the biggest calculation. But for when you are using ETAP, okay, it is only 1 minute job in when you are taking a graph at relay coordination tab in your ETAP. So we will see that one. For instantaneous, okay, for instantaneous settings, okay, what is the formula for instantaneous? This is the instantaneous. Here I am not going to add any intentional time delay here, because this is nothing but load end. This is the end of the network, so it is called nothing but 50 instantaneous. So immediately I have to stop the. So I have to protect my motor. So what is the requirement? As per IEEE 242, you have to add from 125% to 170% of your either locked rotor current, including your asymmetrical factor you have to add, and you have to divide it by, sorry, we don't have any R, okay, this is the one, okay, you have to use only 125% to 170% of your locked rotor current. That locked rotor current, you have to include your asymmetrical factor. Asymmetrical factor in the sense is nothing but while starting, if you are applying three-phase voltage to your motor, so you may not expect all three-phase voltages are in same magnitude, because one magnitude will be in highest and one magnitude will be in zero and one magnitude will be in negative. So due to this effect, okay, there will be one asymmetrical current will be there. So there will be one unbalance will be produced during starting up your motor, three-phase motor. So we are calculating as 1.6 times or 1.2 times. It will be calculated using some electromagnetic transient studies, using some PSCAD or any EMTP studies. If you are done your EMTP study or PSCAD study for your motor, you can able to calculate how much value. But ETAP defaultly is available here. I will show that one. And using this formula, you are going to give here. So as for our current is nothing but our LRC is nothing but 650% we are calculating. So 6.5 into 57.10 is our LRC current. LRC current is nothing but 371.15. So 371.15 into your asymmetrical factor as 1.6. I consider that value also. So now my value is 593.84 divided by your CT ratio is nothing but 70. And you will get your value as 8.48 here, and the curve is nothing but instantaneous, and the minimum value you have to use here. And go to earth fault. Earth fault always we will use normal inverse curve. For this one, this is actually three-phase system. It is nothing but medium voltage. So what is the formula for that one? So you go to your this is actually 51N. 51 is a neutral and this is a 51N. This is actually what we are going to see here. So what is the formula? So ME side, okay, we will consider only 10% because here the earth fault means is nothing but one phase to get grounded. One phase get grounded. During that time, okay, how we are going to give the protection in the phase. In the case of phase protection, how we are going to give. So you have to give the protection against the earth fault protection on your phase side. So how we are going to calculate? Usually in our LV side, okay, we have many unbalance because we are using phase to neutral. Whereas in our system is nothing but MV, medium voltage. In medium voltage, there is no single phase load. All loads are three phase loads. So most probably is balanced load only. But even though we have the point on switching and other issues, so we are, for safety purpose, we are adding 10% unbalance in MV we are considering, and 20% as LV. This is actually our technique what we are using in the industry, and we don't have any considerations. And some standard says with the different wordings, okay, you may consider this much percentage, but this is not the right value, or this is not the recommended value by any standard, to be honest with you. So, and usually in industry, okay, as per the client approval, okay, we are using this value as for 10% unbalance is added in medium voltage and 20% unbalance is added in LV, low voltage. And our voltage is 4.16 kV is medium voltage, so I can add only 10% unbalance up to your full load current. In this case, okay, how much it will be? So 57.10 into just add 10%. So nothing but 5.71 divided by 70 is nothing but 0.08. So here your value will be 0.08 as your setting value. Yes, your setting value is 0.08, and what about why it's not coming? Why the primary amps is not coming? Where is this? Okay, but here it's not coming. You know what's the reason behind? Anyone can get that. When you are giving the value, okay, your relay amp is supposed to be here and your primary amp should be here. But when I'm giving the setting here 0.08157, so I can get 8.82. Unfortunately, I didn't get any amps because my CT value is here 0. Because I didn't give the value here. For CT I have to give the value here. That is the one is major mistake. So I have to configure here is always CBCT value is nothing but 50:1. This is actually there is no relation with what current is flowing through the conductors of which branch feeder or your motor feeder, where you are going to configure this CBCT irrespective of that flowing current, continuous current flowing through that circuit. Okay, we are choosing the value is nothing but 50:1. This 50 is depends on how much current you are limited in your upstream resistance here to the system. Based on your system grounding fault current, okay, how much current you are going to limit it. Based on that, your CBCT rating is chosen. Otherwise, like your phase CT, okay, it's not depends on the continuous current flowing through the circuit. So this is the important point you have to keep in your mind. And if you add this one, if you already configured your CT, so by means of you are adding primary, okay, I'm not going to talk about any class or any board and everything, but it will be detailed discussed in some other sessions, which is CTPT sizing and all. Okay, so during that session, okay, we are going to discuss in very detail, and we have the current ratio and all. Okay, and what about the relay? So in the relay, okay, so now we'll go to the ground setting, so you will get the amps right now because you already give the value of that one. So before it shows reads, it reads as 0, but now it is your amps is very low current as 4 amp. So this is 4 amp current is going to sense by your high sensitive ground fault current, whereas in your phase, okay, the current is it is nothing but 62 amps, whereas in ground, okay, the current is very minimum, this is 4 amps. So this is nothing but high sensitivity is achieved by means of using CBCT. That is the important one. And the instantaneous in ground for instantaneous 50N is nothing but you have to add just full load current divided by your CT ratio. The full load current is nothing but your 57.10 and divided by your CT ratio is nothing but 50, and your setting is nothing but 1.142. So for 57 amps, okay, when ground current, okay, beyond 57 amps, okay, you are not saying, you are not telling that, okay, not necessary to wait, and you can immediately trip your motor. This is your meaning of this settings. So negative sequence is under unit protection, okay, it's not under non-unit protection, whereas your overcurrent instantaneous and the phase overcurrent instantaneous, these are all non-unit protection, or you may call backup protection of motor. So which one is the primary protection of motor is nothing but overload. overload, thermal overload, and acceleration and jam. So here, this is not my topic because these are all under unit protection and even negative sequence under unit protection. But phase and ground, we have 4 operations, is nothing but 50, 51, and 50N and 51. The 4 protection functions are widely called as non-unit protection or backup protection of my motor. So my relay is already setting is over. So I can now have to check my curves is properly fitted in the in between my startup curve as well as my what is it, my thermal distance curve of the motor. So here this is actually, I will explain each and every one. This one, what is this? This one, what is this? You can see when I select this curve, it will read what is this. This is nothing but relay 1. Your phase is nothing but 51 over current. This is nothing but 51 over current. And this is nothing but your IDMT curve. This IDMT curve. And what about this? This also nothing but relay 1. And this is a phase. This is a phase. And this is a 50 over current. That means instantaneous over current 50. This is nothing but DMT. And now these two curves are not integrated. It is in different function and this is in different function. In LV, it automatically integrated together, but in medium voltage, and you have the responsibility to integrate these curves, and you have to block your time over current. This is the IDMT, time over current, by your instantaneous over current. That means that after this point, your time over current will not be operate. Instead of that, your instantaneous will come into the action. So that's why I am going to block that one. Then what will happen? Now the curve shape will be changed as it is. So your current will be going like this. After this one, okay, it will come to your instantaneous. Up to this one, okay, it will fall IDMT because I already blocked that one. So that one, what will happen at this current, it will operate as instantaneous. Here the time is very less. The operating time is nothing but 0.02 seconds. Okay, if I am not blocked, what will happen? You can see. If I am not blocked this one, what will happen? The current will continue flowing. Current will go like this. The current will go like this. Current will go like this. Actually, so practically it will go like this. So it will not block at what? How much amp? This is around 586 amps. Okay, it will not block. So instead of that, okay, what will happen? I have to block it. I have to block it, and I have to integrate these curves. And now I have to choose. I have to take the relay. And one more important, this is actually cold and hot curves of your motor. This is actually motor damage curve. The philosophy is nothing but all your protective curves, any 50 and 51, IDMT and DMT curves, now integrated together. These curves will not supposed to clash with any curve, any starting curve. So you have to adjust the time dial. That is called TMS. That is called time, because time dial we didn't adjust here. We gave only the pickup settings, and we have chosen the curve type, but we didn't touch the time dial, because in ETAP we have an advantage is nothing but just click here. You have to adjust. You have to adjust manually, and it will avoid like this. Okay. So now it is perfectly coordinated. Your motor and your protection curves. Your protection curves is properly coordinated. And here you can use one methodology. So it is not supposed to clash together, but we have some philosophy here. We have to check the time difference between your IDMT curve and your top range of your curve. it should be minimum of your have to minimum 1 seconds you have to minimum. 1 seconds you have to minimum. Here it's nothing but 0.7 seconds. 0.7 seconds you have to use at least 1 seconds. 0.1 seconds. No 1 seconds. This is 2.1 seconds. This is 2 seconds. If it is not possible to able to do it in your curve, okay, go to your what is this? Your TMS, and you can look on. It is just now reduced to 1 seconds, no problem. And even if you want to reduce, okay, you can reduce. That's for point TMS. Okay, for 2, okay, it's not matching, so I can increase to 205. 205 is 0.9, so 209, 209. This is 210. Okay, 210 I can give. 210 is not 209. Okay, so minimum 1 second is I have to supposed to maintain here. For 208, for 208 is around 0.88. So 209.3. So I can at least reach 1.01 seconds. So this is the one, okay, it's the mandatory requirement. Okay, at least you have to maintain. Now your motor is perfectly coordinated with your motor protection relay. Now the next step is nothing but you have to go for your transformer protection. So downstream we are going to add one HV relay. So you have to add a relay here. And you have to add some multi-function relay here. And for relay for CT sizing, okay, you have to open your 10 MVA transformer. And what about the rating? How much current is nothing but 1388. So 1388 into just I'm adding 10% is nothing but 1526. So I can choose 1500 to is to 1. 1500 is to 1 as my CT ratio, and this is here, and this is my transformer. So I can use, this is a phase, and for even ground also I'm using here as 1500. But if you are using sensitive ground fault, you will add some CT in your neutral point of CT here in your neutral connection to your earth. So here we are going to use some CT, and you have to configure with your relay. Then that will call as a sensitive ground fault protection. That is protection is used for transformer under unit protection. Under non-unit protection, okay, we are not going to talk about it. And what are the output? Okay, add any, and add here the second breaker is nothing but CB2. Okay, and overcurrent. And now this is ABB relay. I'm taking that is a protection type. It's not motor. It's nothing but transformer. I'm not going to use any other non-unit protection or unit protection. I'm going to use only the non-unit protection is nothing but overcurrent. And this is RET protection. Okay, I'm going to use the same relay. And I'm not use any ground fault. Okay, I'm using only neutral. Any phase CTs I'm using, because I'm not configuring any ground CT here, like what I did in motor. But here I'm using only the neutral. Okay, for that I'm going to give the settings, and I will give the coordination between the downstream relay to upstream relay. Then I can wind up the class session, I think. For this one, okay. This relay doesn't have any IEC curves, because this relay is RET 541. I'm not sure. I don't have anything. So for that, instead of that, I'm going to choose some other relays. 615, RET 615, that is RET 615. RET 615, yes. 615 is this, yes, okay. RET 615, okay. I have all relays. So you have to ensure, okay, your relay has all curves. So you have to choose this one. So for the transformer secondary, okay, you have to go to the slide and you can check the value of that one, because we have very limited time. We have limited time and topics are we have very much. And this is the LV side. Okay, this is LV side. Yes, LV side. Okay, this is LV side. Okay. Okay, this is LV side. Okay, LV side for 51. Okay, the same philosophy what we have saw in our motor. 1.1 of your full load current of your transformer, and you have to give the CT primary. So here, what is your full load current of your transformer? It's nothing but it's showing different. It's not the one. Actually, you have to choose the value here. What is this? How much? It's I think 1388 into 1.1 divided by your CD ratio is 1500. So the setting is you see, I'm choosing here is a long inverse, extreme inverse. Let me check. We will change at any time by means of this one, and the value, the relay 2 still is why is showing as a motor relay. It's not supposed to be motor relay. This relay is a transformer relay.
Sheikh sir.
Yes.
Sir, in that we can choose the protection type.
I think the protection type is wrong. The protection type is wrong, so I will do that one.
From that we can pick it.
Weighted type. I think this is a transformer was chosen. Okay.
Yes. In the transformer overcurrent, so it is in filter out. So filter on you can choose it. Yeah.
One device parameters still doesn't change its value. To be honest, the still is showing induction motor. It's supposed to take the current value of this motor. I will do that one. Okay. Spread okay. Output okay. Okay, this is the circuit breaker 2, I think. Okay. Fault is coming. There is some fault here, I think. Device parameter still showing. Default is considered your motor. It's not supposed to be like this actually. See, it's already default is takes as it is 615, okay. Device ID, need to. Wait a minute, let me check the relay value.
Sheikh sir?
Yes.
I got a call, that is why it got disconnected.
Okay.
Yes, sir. Actually, time is like 6:30. Probably we are spending 30 minutes for the question and answer.
Okay.
Yes, so the coordination we have done that we can finish that is a request from the side.
Okay, I will show that slide actually. This is actually the way I will explain, because the heat up sometime I have to restart the heat up. This is actually the value, so we have to give the value of 1.1, 10% of your full load current of your transformer, and this you have to choose normal inverse or standard inverse, and you have the TMS. You will see the downstream TMS, and you have to give your pickup settings. And if your downstream you have the motor, so you have to consider the 80% of that, and you have to asymmetrical factor you have to include, and you have to give the 30% additional margin. and you have to give the settings. This is nothing but instantaneous, and you have to give the time dial as per the your downstream. And 51N, okay, this is nothing but actually this is LV, so that's why they are considering 20%. But in our case, it's nothing but MV medium voltage only, so you have to add only 10% because this is LV mode, LV side of this one. This slide shows. So they have considered 20%, but ours is medium voltage 10%. We have to add like this. And 50N, okay, full load current of the load. Okay, you have to give the settings. And finally, this is a relay parameterization. Okay, they are calculating and they are giving the value. And finally, they will get the curve like this. They will get the curve like this. Okay, we get the curve like this. And for earth fault, okay, for earth fault protection also, if you click the earth fault here and you get the earth fault curve like this. And this is the conclusion. Okay, we will have the settings for that LV set of the motor. And this is the scenarios. And once you have done all this function, okay, for example, I will choose some other relay. I will some other relay. There is RET 615 function as overcurrent. RET 615 as 620. I can go with normal inverse curve. Okay, and this is actually 1.07, and the neutral is normal inverse, and the instantaneous is nothing but I have to go with 1.3 into your downstream settings. How much you have? Downstream settings is about 593. So 593 plus 400. You have to add something. So 1.2 divided by 1500. 0.86. 0.86. So 0.86 is not supposed to give, so you have to go with 1 only. Actually, this value will not supposed to be 1, okay, because of it's not really correct value here. That's why it is considered only 1. It's supposed to 0.08, 0.896. So I'm giving 896. So this is my overcurrent settings. Yes, okay. And this normal inverse only 10% of your flow current is 1380, and roughly one current divided by 1500. So just for coordination purpose, 0.09. Okay, and this is actually I can give only 1 because I have any option. So now what I have to do? So first I have to this relay, and I have to go for relay coordination and check the relays are properly coordinated or not. So this relay has some other protection function is enabled. That's why this is coming. This demo over relay. Okay, I remove this one, and I don't want differential also. Okay, for motor, and I have to integrate these curves. Okay. Okay. So now this is the relays. And whether it's for this is the relay 2 is my transformer relay, and this is relay 1 is my motor relay, downstream relay, and we have to give the coordination time interval between that. Okay, we have one topic here. Actually, I don't have time to cover this one, and I will explain very shortly. There is a coordination time interval. Okay, that is called. What do you mean by the coordination time interval? Means from downstream to upstream. From downstream to upstream, you have to add, there is a coordination time interval. We have to add some coordination time. That's 200 milliseconds. So let me finish within 10 minutes. Okay, we add 10 minutes because we have started 15 minutes late. So I will take the time, to be honest with you.
Okay, sir. Okay.
So this is at load end. So we are not giving any intentional time delay because we are adding instantaneous as immediately. You have to clear the fault. But when you are going one stage to other stage in the bus, okay, from downstream to upstream, when you are going to the relay, so you have to give your coordination time interval between these two relays as minimum is required by the standard is 200 milliseconds for numerical relays. Different relays has different timing, but nowadays modern technology is nothing but numerical relays, which is microprocessed relays, and has 200 milliseconds minimum critical and minimum coordination time interval is required. Whereas if you use any electromechanical relays or any your static type relays, okay, the time will be higher, more than any. It will be minimum 400 milliseconds between you have to maintain between these two relays. Yani after this relay, my relay 2, okay, once relay is operated, that yani 2 is operated, if the breaker CB2 is failed to operate, then after 200 milliseconds, my relay 1 has to operate. This time coordination between two relays is widely called as coordination time interval. So that one, okay, how we are going to achieve here? By means of, okay, this is our downstream, okay, you are not supposed to touch that one, okay, you already said that one. Go to your relay 2, okay, this relay 2 has your time coordination between this. So these two relays has time interval, coordination time interval between that. So that is nothing but 200 milliseconds. So here they use this time difference tab, and you can check that time is achieved or not. So now time is nothing but only 170 milliseconds. So our recommendation is nothing but 200 milliseconds. So now 250 milliseconds. I can reduce 210 milliseconds. I can adjust now 210 milliseconds. 200 milliseconds is maintained. This is the what is nothing but coordination time interval between your downstream to upstream. Okay, you can now you can check your coordination whether I achieved or not. Now what I'm doing is actually fault insertion. I'm going to insert the fault. Okay, either I can insert three-phase fault, or I can insert line to line fault, or line to ground fault, or line to ground fault. Any fault I can insert here. So I'm going to make the fault here in motor terminal. And what about the sequence? So first my breaker is operated, then my second breaker is operated. So I can see able to see my sequence viewer. So here at 20 milliseconds, my relay 1 is pick up for the fault current of 808.94 kA and 20 milliseconds T1, because we don't have T2 here, because relay has repeatability capability. Modern numeric relay has in medium voltage that we are using, that relay has repeatability capability, and it doesn't have any band. Whereas if you go to the release, LV circuit breaker, it has band like fuse. We cannot expect, okay, it will operate at particular time of operation or particular current, and the current and time of operation will be differ, and there is band between lower limit and upper limit in case of fuse and the lower LV breaker. In case of HV, okay, we don't have that, we don't have anything. So that's why the T2 is empty here, and we have only T1. So at 20 milliseconds, my relay overcurrent 50 is activated because the fault current is high. That's why the instantaneous is operated first. Because when fault occurred, okay, immediately my breaker going to, and my relay going to operate. This is actually my philosophy. So instantaneous is operated, and it is stripped by, and my circuit breaker is stripped by my instantaneous overcurrent relay of relay 2, and the time is after 20 milliseconds. So breaker clearing fault, okay, it takes around 40 milliseconds. This 20 and this 20 is now the time is 40 milliseconds. And after coordination time interval, because we added 200 milliseconds here. So after 20 there is added 200 additional. So after 220 milliseconds, my relay 2 is operated at what? At overcurrent 50, because here the time overcurrent is already blocked by instantaneous overcurrent. So both relays are operated in 50 because it's already blocked by this one. So in this case, okay, after 20 milliseconds, because breaker operating time is 20 milliseconds here, but in some time the breaker operating time will be 40 milliseconds. Means okay, this time will be increased. So totally 240 millisecond is enough up to my motor to your transformer downstream is clear the fault. clear the fault. This is the actually relay coordination. So you have to do proper relay coordination and you have to achieve the lowest time of operation. So lowest time of your any fault clearing time you have to achieve here. That is the important thing. Based on that, okay, you are going to design your what is the switch gear short time rating and breaker short time rating and your arc flash necessities of each and every bus, this bus and this bus. What will be your arc flash requirement, and you are going to calculate the incident energy, and you are going to calculate your arc flash boundary, and what about the working person's any personal protective equipments category. All these things, okay, you are going to calculate based on this time. So how much time you can able to clear the fault by means of tripping your circuit breaker. So this time will be subjected to your relay and your which curve you are chosen, and what about your settings and where you have placed. All these things will be playing a vital role to choose these locations. So now I hand over the session to Bala. So he will be answer your questions if you have any, and there is any matters to be discussed. Okay, we will discuss. Bala. So audience, you can ask a question. Okay, myself or Bala will answer. So from my end, okay, this is actually relay coordination. What we are seeing. So this is actually basic. We will not cover. We don't have the time to cover all other important things, but maximum important matters have been covered.
Sheikh sir, thanks for your timely help. Because of my poor internet and Sheikh sir able to manage instantly. I would like to say thanks to Sheikh sir, our principal engineer from Power Projects, and he has some vast experience around the world. So probably audience, if you have some any doubts, you can ask whatever it is. So since we are talking from education industry to the industry, education industry to the, which means like a practical industry, so we have some long gap. Long interval, like long space we have. So that is the maybe, and so however we are discussing with some ABB typical relay model by using that, how we are going to coordinate and how we are going to protect your motor transformer as well as according to your standard. So maybe in future if you are go through some standards, and you will understand more. And if you have some doubts, please ask, and our Sheikh sir is there, and myself is there. We have some doubts, and we able to clarify you. And yes, we are looking for some questions. You can directly unmute and you can ask any doubts. Sheikh sir, are you there?
Yes, Bala, I am here. Actually, I am looking for a chat box. Is there any questions are there? If someone is not ready to ask, okay, at least they may able to type it in their chat box. Even very basic questions, simple questions you may ask, which is related to our relay coordination topic. Even maybe in your microgrid, or because the source is nothing but microgrid, okay. And relay coordination, you have to start from your motor to your source. That's it. So I consider my grid as the microgrid.
The quick facts we have to understand from our Sheikh sir lecture. So can you able to tell motor taking how many times of current initially? Anyone? So far in this lecture, we have to understand.
I think in our machines, we already read about it. I think the motor will take around 6 to 8 times of full load current. Am I correct, Bala?
Yes, sir. You're perfectly right. So
I think our professors and assistant professors can able to give the. I think this is a very simple thing. I think they know very well, and I think they are expecting some answers from some other participants. I think. Some other questions, Bala, you can ask to our participants. If they are not asking the question, okay, we will ask the questions to them.
Yes. So that is why I'm asking, because the motor is taking typically 6 to 7.2 or like 8 times of our current. So if it is a normal motor, if it is energy efficient motor, normally take 10 to 12 times of initial starting current. So during that time, our power factor will be low. It will consume high reactive power. So that is why the reactive power management is one of the very typical topic while talking about the power industry. And so that is the thing.
What about the starting power factor for DOL starter? If you are using DOL starter, what will be the starting PF of my motor?
Yes, sir. You are asking to me or to the audience?
Audience. I think you are very familiar with that.
Okay, whatever maybe, and no problem, sir. And if we get some chance, and directly we can able to deliver our lecture in our college itself, and if time permits. Chintamani ma'am?
Yes, sir. I'm here, sir. Yes, sir.
Okay. If there is no questions from our audience, and
we can.
Yes, Nagalakshmi ma'am already answered. Okay, it is very low power factor.
Okay,
yes,
sir.
Nagalakshmi ma'am, it's approximately. Thank you.
Ma'am, Nagalakshmi ma'am. Ma'am.
Sir, thank you, sir, for the valuable session, and I thank the participants too for your kind cooperation for making this event a grand success. Thank you, sir, for your valuable session, and thanks for sharing your valuable time and sharing your knowledge, sir. Thank you so much.
Thank you. Thanks to all of our participants, and especially my colleague Bala. Thanks, Bala. And thanks
Thank you, sir.
Thanks, ma'am. And Nagalakshmi ma'am. Okay.